A great way to familiarize yourself with these vector concepts in a real world context here is just to think about a simple physical application. So here I have some sort of particle that's moving along a straight trajectory, along a straight line. It has constant speed, and I first observe it at this point P, whose coordinates have been given to us, and then 5 seconds later I observe it at this point Q, whose coordinates are 4, 4, and 4. And we'll just associate many of the operations that we've done with vectors thus far with certain physical interpretations. So the first thing is, what does that vector PQ represent? It's going to be the observed displacement, the displacement of the object over that 5-second period. So P to Q would be the change in those coordinates. And remember, I end at Q and I start at P, so I go 4 minus 1, 4 minus 2, 4 minus 3, and I get the vector 3, 2, 1. And each one of those quantities was a length, so those components all have lengths associated with them, and so we would think of that vector as being a vector with units of meters attached to it, or rather, each component has meters attached to it. If I calculate the length of that vector PQ, I sum up the squares, so 3 squared, 2 squared, plus 1 squared, I get 14 squared. The square root of that is the length, and that is actually the distance traveled in meters by this object over that 5-second period. So the length of the vector is the actual distance traveled, at least the observed distance, assuming it's moving along a straight line, doesn't stop at any point. If I want to find the velocity of this vector, or I'm sorry, the velocity of this particle, what I would do is take that displacement vector, which represents change in position, and divide it by the change in time, and that was observed to be 5 seconds. So I would take PQ and I would scale it by a factor of 1 over 5. So that means I'll call it V for velocity, and it's 3/5, 2/5, and 1/5, and that's a vector. Each of those components have units of meters per second. If I find the length of the velocity vector, I get what a physicist would call speed, the magnitude of the velocity vector. And we can calculate the sum of squares there, 9/25, 4/25 plus 1/25, sum that all up, and I think you get the square root of 14 over 25. So square root of 14 over 5. Not a huge shock, because what are you getting here? You're taking that displacement of square root of 14, that distance traveled, and you're dividing it by 5. Same thing as taking PQ and dividing it by 5 and finding the length of that, which is exactly how we got this vector. Of course, that would have units of meters per second because it's velocity. If I look at direction, and remember we defined direction to mean the unit vector now, what I'm going to do is normalize either the velocity vector. Velocity is pointing in the direction of motion, so I would normalize that to get a unit vector. That's the same thing as taking v over the length of v, but I could also just take the displacement and normalize that. They would both point in the same direction, so the normalized vectors would be the same. The unit vectors would be the same. So in this case, I would take 3, which is the component here, and divide by the length of PQ, which was square root of 14, and do that for the other components. This gets me a unit vector, a vector of length 1 that points in the direction of motion. And notice what happened here is that, yeah, it's a unit vector in the direction of motion, but more importantly, by normalizing it, we removed any physical units. So 3 was a unit of length in meters, and square root of 14 was a unit of length in meters, so this component has no units attached to it. And so these unit vectors, and when we normalize to get a unit vector, these are always going to be dimensionless quantities. In other words, any physical units that were attached to them have now been lost. And that's important. It's simply conveying direction. It's not conveying a magnitude of any other physical quantity.